All right, hello everybody. Welcome to 10.6 day one. We're going to be looking more at vectors, and we're going to be looking at vector operations and direction angles. So today we're going to talk about unit vectors and perform operations with something called the linear combination form of a vector. And then we're going to find the component form of vectors given a magnitude and direction angle. So in the previous section, we discussed vectors, and like our supervillain from Despicable Me, a vector is a quantity that has both magnitude and direction. So we're looking at something that has magnitude and direction. All right, so these vectors can be written in component form, A comma B with the pointy brackets. And remember, A is the horizontal distance and B is the vertical distance, kind of like X and Y in the coordinate plane. Magnitude, remember, is the length of the vector. And if you take a look at your formula sheet, this is all on your formula sheet on the back, the length of the vector, magnitude represented by those double bars, is just like the distance formula or like the Pythagorean theorem, square root of a squared plus b squared. And today we're going to look at our direction, and direction is represented by the angle theta, and it's going to be between 360 or 0 and 360 degrees. So if we're going to be using our calculators, and what you're going to want to do is make sure your calculator is in degree mode. So find that mode button, scroll down, make sure degree is highlighted. Up until this point, everything we've done has been mostly in, since chapter 6, mostly in radians. So make sure you switch that back to degrees. So let's get started. We're going to be talking about a unit vector, and all a unit vector is a vector that's length 1, hence unit. Remember, we think unit circle. The unit circle has a radius of 1. A unit vector has a length of 1. The most common unit vectors are 1, 0, 0, 1, negative 1, 0, and 0, negative 1. We can prove that these are unit vectors by finding the magnitude of each. So just as a quick example, the magnitude of this first vector here is going to be square root of 1 squared plus 0 squared, which just gives us the square root of 1, which is just 1. And you should be able to see, even without doing that algebra, that then the magnitude of each of those would also be 1. All right, so show that this vector, which should say 3/5 and 4/5. So there's the component form of that vector, 3/5 and 4/5, is a unit vector. So in order to be a unit vector, your magnitude has to equal 1. So we're going to find the magnitude of u, which is going to be the square root of 3/5 squared plus 4/5 squared. That's going to be the square root of 9/25, squaring both the top and bottom, plus 16/25. And that's equal to the square root of, if you add those together, 25/25, which is the square root of 1, which is in fact 1. So therefore, it is a unit vector. Showing that something is a unit vector is pretty straightforward, but what if you're given a vector and they want you to find the vector u that has the same direction, but it is a unit vector? So in order to do that, first, let's figure out what the magnitude of v is. So the magnitude of v is the square root of 5 squared plus negative 12 squared. So that's the square root of 25 plus 144, which is the square root of 169. Oops, which is just 13, not the square root of 13. Okay, so the magnitude of this vector right here is 13. So in order to get the magnitude to equal 1, we would need to take 1/13 of that. So u is going to be equal to 1/13 of v, which is just scalar multiplication, 5/13, negative 12/13. And if we check that, magnitude of u should be 1. So that's going to be the square root of 25 1/69 plus 144 over 169 equals the square root of 169 over 169, which is the square root of 1, which is 1. Okay, so our unit vector that is going to have the same direction as v is going to be 5/13 negative 12/13. So in general, what you're going to do, if you have a vector v and you want to find the unit vector, all you have to do is multiply that vector by 1 over the magnitude of v, and that will give you the unit vector. Another type of vector notation is something we call linear combination form. And that just involves using these two vectors I and j. I is going to be 1, 0, and j is going to be 0, 1. So if you have a vector that's given in component form, 6, negative 2, what we do is we break that into two parts. So we break that into 6, 0, and 0, negative 2. If we added those two together, you'd get 6, negative 2. And then we take out a scalar multiple. So here we factored out a 6, and here we factored out a negative 2. Now, I is 1, 0, j is 0, 1. So, therefore, this is equal to 6i plus negative 2j or minus 2j. Okay. So, in general, to get the linear combination form, you just take the component form AB and rewrite it as AI plus BJ. So our first example using this is, first, we are going to find 2u plus 3v, and we're going to write this answer in component form and linear combination form. So I'm going to start with linear combination form because it's already in linear combination form. So 2u is just going to be 2 times 3i plus 2j. And then 3v is just going to be 3 times 8i minus 4j. So if we distribute the 2u is going to be 6i plus 4j. 3v is going to be 24i minus 12j. And then we can combine our like terms. So 6i and 24i is 30i. 4j and negative 12j is a negative 8j. So this is our linear combination form. To get that into component form, written in green here, that's just going to become 30, comma, negative 8. So linear combination form is AI plus BJ, and then we just take the A and the B and put it into our linear combination form. All right, the next type of problem is using direction angles. So direction angles have to do with the degree measure that that vector has strayed from our starting point here, this x-axis, or the degree of rotation that it's moving from there, and that tells us the direction, because then we'll be able to know what quadrant it is in based on the degree measure. So first, here's a diagram. The vector here is in purple, and remember the magnitude of that is the length, so magnitude of v. And then theta here is kind of encompassed by this right triangle formed by the A and the B components. So if we look, sine of that angle, or the sine of the direction that this vector is going to be opposite over hypotenuse, so B over magnitude of the vector. Cosine theta is going to be adjacent over hypotenuse, so A over magnitude of V. And then tangent theta is opposite over adjacent, so B over A. So these are going to be helpful to remember. Most of the time we're going to be using tangent, but then we'll also get into kind of where the sine theta and the cosine theta come in very helpful. So we are going to have to pay attention to what quadrant the vector is in. So we're going to want to remember reference angles. And that's what this diagram here is reminding you of. All right, so find the direction angle of each vector. Make sure your calculator is in degree mode, like I said at the beginning. So first, it's helpful to sketch a diagram so you can see what quadrant that our vector is in. So we are looking here at 3, 7. So over 3, up 7, we're in quadrant 1. Okay, now our angle here is going to be right there at the origin, theta. So to get theta, we have the opposite and the adjacent side, the 7 and the 3. So we're just going to use tangent theta equals opposite 7 over adjacent 3. And then to solve for that, we do the inverse tangent. So theta equals inverse tangent of 7/3. Now this is a great time to check and make sure your calculator is in degree mode. So you do second tan to get that inverse tangent function, 7 divided by 3, and I got 66.8 degrees. And our angle or our direction is in quadrant 1, so 66.8 degrees, that is in quadrant 1, because remember we're comparing it to our reference angles. All right, next we're looking at the vector -4, -2. So if we draw our picture here to help us out, -4, -2 is going to be left 4, down 2. So we are over here in quadrant 3. So theta is there at the origin. And this time we'll use tangent again. So tangent of theta is opposite -2 over adjacent, -4. So we are finding the inverse tangent of that, simplifies down to 1/2. -2 over -4 is positive 1/2. So in your calculator, second inverse tangent of 1/2 is going to give us 26.57. I'll just round it up to 26.6. Now, is the angle 26.6 degrees over here in the third quadrant? I'm hoping you're saying no. So what we need to look at then is, okay, we're over here in quadrant 3, and 26.6 is over here in quadrant 1. So if you look here, especially since we're just using tangent, remember the other solution is 180 degrees away from that. So what we're going to want to do is add 180 degrees to this, so that we are in quadrant 3. So if we do that, we get 206.6 degrees. Okay, because we wanted the angle over here in quadrant 3, and if you think of reference angles here, 0, 90, 180, 270, 360, 206.6 is between 180 and 270 over in quadrant 3. So then your answer will make sense. All right, so now we're just doing essentially the same thing, finding direction angle of each vector, only now our vector is in linear combination form. So what I suggest doing is rewriting this in component form. So this is actually in component form 3, -7. Because remember, this is A, this is B. Okay. Then what you're going to want to do is sketch a picture to find that direction angle. 3, -7 is going to be right 3, down 7. So we are over here in quadrant 4. So at the end of this, you're going to want to make sure your answer is in between 270 and 360 degrees. So now to find this, we're going to do tangent. So tangent theta equals opposite over adjacent, -7 over 3. Theta is the inverse tangent of that. So second inverse tangent of -7 divided by 3 is -66.8 degrees. Now, -66.8 degrees is actually going to be the angle going this direction, but we want to come back around the positive way here. So what we need to do is basically just go once back around to get to the positive version of that angle. So what you're going to do is just add 360 degrees to that. It kind of shows up here in the reference angles. If you have a negative theta, you're going to add a positive 360 to it. So your theta is going to be, if you add 360, 293.2 degrees. All right, so this next one, I'll help you get it set up into component form, and then what I want you to do is draw the picture, find theta, and then make sure you have theta in the correct quadrant using your reference angles. So this vector in component form is -4, 2. Now I would like you to pause the video here, see if you can work out the solution, and then check back in when you're finished to see if you got the correct answer. All right, so hopefully you paused, started up your video again here, and here's our solution. So we started out, tangent theta is -2/4. When you did the inverse of that, you get -26.6. -26.6 degrees is over here in the fourth quadrant. It's negative, so it's a left rotation, 26.6 degrees. So basically, and remember tangent, repeats every 180. So to get to the angle mirrored over here, you just need to add 180 degrees to it. Here's your clue right here also. Negative theta plus 180. So we got a negative angle, so we're going to add 180 to get over in quadrant 2. So you should have gotten 153.4 degrees if you added 180 to that. And a good way to check is 153 degrees is in between 90 and 180, which is in quadrant 2. All right, so now we're going to combine things a little bit, find the magnitude and direction angle of each vector. So to help you remember a little bit, magnitude, remember, is the square root of a squared plus b squared. So the magnitude of this vector is just going to be 12. Now, what we want to do is, you might be feeling like, I'm pretty comfortable, I just know I'm going to do tangent. But let's take a look at this picture first. This is why it's always helpful to sketch it out first. Vectors are easy enough to sketch, so let's just do that. So this vector is 0, 12. So we are going up here to 0, 12. So essentially what we did is this angle rotated just to this vertical axis, the y-axis there. And that is actually just 90 degrees. So this one you don't even really have to do any necessarily work on. You are just going to look at it and say, oh, I know that's 90 degrees, okay? So you got your magnitude and your direction angle. All right, next, let's find the magnitude of V. So magnitude of V in this case is going to be the square root of -8 squared plus 0 squared, which ends up being 8. And this one too, let's just sketch it out and see if we can get our direction angle by just looking at it. So this one is -8, 0. So you go left 8, up 0. So there's your -8, 0. Well, to get there from that x-axis, you go that straight line. So that would just be 180 degrees. Okay. So if they're on the axes, so if it's on the x-axis, if it's on the positive or negative y-axis, you can just tell what your degree or what your direction angles are going to be based on the fact that you know each of these angle measures. Okay? All right, next, what if we are being asked to find the components? Okay? So we're going to use this idea down at the bottom, but let's just kind of see where that comes from by using the triangle drawn here. So we know the vector has a magnitude or length of 30, direction angle is 10, and we need to figure out A and B. Well, it's kind of just like solving a right triangle. So to get A, let's say, we would need to use A and the magnitude of 30, so that would be cosine. So we're going to think, okay, cosine of our angle 10 degrees is going to be adjacent over hypotenuse. Okay. To solve that, we would get A equals 30 times cosine of 10. All right, to get component B, we would use opposite hypotenuse, so we would use sine. So sine of 10 equals opposite B over hypotenuse, 30. And then B would be equal to 30 times sine of 10 degrees. Okay. And you could simplify that into decimals, or what you're going to find that we do is we just leave that unsimplified, because 10 degrees isn't a nice number, a nice angle measure on the unit circle that we know cosine and sine easily of. So we're just going to say that this vector, the components are 30 cosine 10 degrees and 30 sine of 10 degrees. And kind of like cosine relates to the x-coordinate, sine relates to the y-coordinate, you can kind of remember that here with components, right? To get A, which is your horizontal or quote-unquote x-coordinate, you're going to multiply the magnitude by cosine of theta. And then to get B, you're going to use sine, because B is like your y-coordinate. So B is going to be magnitude of V times sine theta. So let's try this here, a little practice. So find the components of a vector that has a magnitude of 12 and a direction angle of 150. Well, simply enough. To get A, we're going to do the magnitude of V, 12, times cosine of 150. And then to get B, we're going to do the magnitude times sine of 150. Now this one is kind of nice because cosine of 150 and sine of 150, that's on the unit circle. So I'm just going to use what we know about that. So our components here are going to be 12 times cosine of 150 is negative root 3 over 2. And then 12 times sine of 150 is 1/2. And then just simplify. So this becomes 12 over 2 is 6, so negative 6 root 3, comma 6. So when possible, use your unit circle. If not possible, just leave it like we did in the previous slide. All right, that about does it for some more vector operations. So go ahead and give the 10.6 day 1 worksheet a try, and then see if you can tackle that daily task on Schoology. Have a great day. See you guys for day 2.